Right, thanks, Vaughn, and hello, everyone. Like I said, do let me know if my microphone suddenly stops working. I've had some issues, but it should be fine. And yes, as Vaughn said, this is the first time I'm presenting a paper, and my background is more classical, I guess, than the usual machine learning or AI researcher, in that I started with classical frequent statistics and then went on to Bayesian statistics after that. But it all depends on where you draw the line. I guess a lot of AI research is also Bayesian in nature, but a lot of the models I'm familiar with and work with a lot are ones that come from the insurance world that usually require some kind of, I think the correct term would be generative modeling, basically, as opposed to using non-parametric classification models. So this paper, based on big data, the consensus Monte Carlo algorithm, as Vaughn said, it's quite old. It's a paper from 2013. But I think this is one of the really useful ones that I don't think has received enough attention, because it opened up one of the issues that we've been having in Bayesian statistics and complicated Bayesian models. Is it's not that good to deal with big data, as in it doesn't scale. The estimation algorithms never lent itself as easily to, let's call it, batch processing as some of the more machine learning or AI algorithms. And therefore, I think these kind of models have almost taken a back seat in industry and academia. I think this is one of the papers that started the change. It's certainly a big one. I know in 2016, another one came out that essentially implemented this in R, implemented these methods, making it quite easy to do consensus MCMC. But yeah, this is essentially the article that started making a lot of the Bayesian models that you can estimate using probabilistic programming languages like Stan or PyMC or JAGs or bugs useful, because you could actually run it on very big data sets. So I'll start going through it. But the main takeaway from this is big data used to be a problem for Bayesian models. This article sort of made the problem embarrassingly parallelizable, or pleasingly parallelizable, depending on whether you're a glass half full or glass half empty kind of person. And in the intro here, they say essentially one thing you can do, or I guess if you've got big data, a lot of statisticians have said, well, it's not really a problem if you have data too big to fit on your computer, because you can always take a sample of it, right? This is what we've always been doing. This is what frequentist statistics is all about. What do you do if you have a sample of a population and you want to learn something about the population without analyzing all of the data, basically? But in writing that off or hand-waving it away, I think they missed out of a lot of the useful things that come out of big data. A classic example, and this is actually where this research comes from, is if you have something you want to identify, an effect that's really hard to identify in a small data set, essentially. Like if you have millions and millions of clicks and you actually want to see what makes a person more likely to click on your ad, where a click event is already so rare, basically. How do you estimate those parameters and find them to be significant if in all your samples, your parameters show up as insignificant, needs more data, basically? So that's the one way people have dealt with big data, is to say, well, you don't have to analyze all the data, you analyze a sample of the data, basically. Another way is doing the breaking it up into small parts and doing it one batch at a time. This is what AI is really good at, is that batch processing, running over and over and over the data and updating your hyperparameters and your parameters one batch at a time, basically. This is a technique that works if you're doing back propagation and like estimating the parameters in that way. But this isn't a technique that's readily available or accessible if you're doing ordinary, let's call it classical statistical analysis, or like they call it in here, traditional statistical analysis in the introduction. You'll see here they mention that here somewhere. And what they mean by that is when you have a likelihood that you either want to maximize or that you might be a Bayesian and you multiply it with a prior. So here in the intro, they just lay out the problem and they say, well, if you decide that you want to split up a problem, you can either do that by splitting it up onto multiple cores into GPUs, or you can split it up to multiple machines. It's what they discuss here. And then they highlight and say, well, the issue is when you do it like this, oftentimes your issue is how do you communicate in between the devices? And they lay out here a theoretic example where they say the issue isn't in your problem being too hard to estimate on one machine. It's more when you start splitting it up into the machines, all the gains you make in efficiency, you lose in the machines having to communicate with each other. This is if all the machines work on the same problem essentially, and you have something that's not embarrassingly parallelizable, where the cores or the GPUs have to communicate with each other essentially. So that's the problem. And then they say here, well, what they do in this article is they rewrite the problem of likelihood-based inference, especially in the Bayesian one, to make it easy to spread out over machines so that the machines don't have to communicate with each other. That's mainly what they say in the intro. And they say what they do in the section, in each of the sections, basically, which we'll go through. In section 2, they just prove, I guess, in inverted commas, that if you have a difficult, well, not even that hard a problem, this is a binomial model, you could also think of this as the first layer in a neural network, basically, because you just have the binomial model or the logistic regression model, and then a logit function that you link up to your predictors, basically. So we focus on a single layer hierarchical logistic regression model, and then they just lay out the problem in a way that they show if you try to be smart on a single machine or spreading up the problem as a whole, the main issue you run into is actually the waiting times for the machine to communicate. So that's what they say here. In the conclusion of this section is we wish to emphasize that time is not lost in what one might think are the obvious places, basically. It's all about communicating. So if you want to actually address this issue, you need to make the problem embarrassingly parallelizable. So interesting here again, this article focuses on the Bayesian model. So if you were, let me annotate quickly. If you were a frequentist, or if you were doing machine learning, this would be draw. Let's try to draw this. This would be your model, basically, logistic regression, or for that matter, a neural net with one layer, basically. Up to here, the frequentist and the Bayesian, and I guess the machine learner would agree. This is the model. This gives you the likelihood. If you are a Bayesian, all you have to do is then essentially assume a prior on all of your unknowns, and now you are a Bayesian, basically. That's the difference. Frequentists and Bayesians usually agree on the assumptions. They don't agree on how you should estimate the parameters. So this is what makes the model a Bayesian thing. And in doing this, also usually where you introduce all kinds of complexities that make the model, let's say, non-parallelizable. So if I clear this, we can go on. That's essentially all they're saying in this section here, is that things are hard. And even if you try to be smart about how you split up the problem and how you divide and conquer, you might lose all the efficiency gains in communication gains, basically. So next section, this is where they say the idea behind consensus Monte Carlo is essentially to get as close as you can for a Bayesian model to, let's call it, batch processing, where you only do a small piece of the data at a time. They call these pieces shards instead of batches. And I think they don't use the machine learning or the AI words on purpose, because you don't have to do a pass on all of the data. You could still only do this on a sample. And the way you choose the shards, as you'll see later in the article, is quite non-trivial, and you need to be careful about it. And also, you don't run through, let's say, your batches in theory. Like, you don't do batch 1, update your parameters, and then go on to batch 2, update your parameters, and 3. You can run all of them in parallel, basically. I see someone raised a hand. Is there a question?
Yeah, it was me. I just wanted to ask your clarification from your opinion there, because why do you think using the term machine learning or AI is a problem if you are working with shards? You mentioned that, and I didn't understand. I don't get why.
Yeah. Why is it a problem?
Yeah, but why would they not use it? Because you said because they are using shards.
Shards, yes, yeah. Well, so usually the term is usually batches, right? That's what you do. You run your data in batches. I think here they avoided the term batches on purpose, just to contrast this method to the usual one of batch processing. I don't think it would be a problem. I think it's just for them to avoid all confusion, basically, if it makes sense. You could call them that. You could say we're doing them in batches, but I think they chose this word on purpose, essentially. If the method was exactly the same as in the machine learning or the AI case, they could just call it a batch, basically. This is just my opinion. Like I said, I don't think it's a problem. I think it's just them trying to be clear that even though the method is the same, like you run it on small batches of the data, they use the word shard on purpose, basically. And I think that's why. I might be wrong. Maybe they weren't aware of the literature.
No, that
couldn't be one of the reasons that the shard sort of signifies that the data in the shard is co-located, but not data in between shards, right? So typically sharding means that like, the machines themselves are separate.
Yeah, exactly. That could be, and you can run all of it in parallel. So you essentially break your data into shards, run everything in parallel, and you didn't recombine it. I just found that interesting that they called it shards and not batches, and I think this is why. But I might be reading too much into it. Shards, so as not to say that this is all restricted to the AI community. Is it that they call it shards so as not to say that this is all restricted to AI community? It might be, like I said, I might just be reading too much into this, but it was interesting to me. Give each shard to a machine, and then it does full. So essentially what this is doing is you take like I said early on, if you were a statistician or a frequentist and you had a data set that was way too big for your computer, you could say, well, we don't need to analyze all the data. We could use a sample of the data. We could treat all of the data as the population, draw a random sample of the data, and just estimate from the sample. Problem solved. The issue is you don't have to do it like that because you have all the data. So you might say, well, we can resample. We can do this 100 times. Or if we take a 1% sample, we can redo the analysis 100 times, and then we have 100 estimates of the parameter, basically. Now you can actually start checking frequentist sampling theory. I guess what this is making smart is it says, yes, we can do that. But if we have all of this, let's say we have 100 estimates of our parameters, there must be a smart way to recombine the 100 estimates as one would in a meta-analysis. If you analyze a thing over and over and over, you don't want to throw away everything else. You need to be able to combine combine it in a smart way to update your beliefs, as it were, and see what is the actual consensus. In a meta-analysis, oftentimes you might have 4 studies that neither of them found anything significant, but if you combine them as a meta-analysis, now the result becomes a significant one because you didn't have enough information or a large enough sample in each of the individual ones, but if you combine them, you get a significant result. That's essentially all this article is doing, is it says we split up, we get individual estimates, and then how do we recombine them in a smart way? And this is why it's called consensus Monte Carlo. It's quite smart, actually, and I'm surprised they didn't think of this sooner, and also that it hasn't made more like waves in the community, I guess. But this equation number 2 is essentially what makes this work. And the important thing here is this: you assume this independence structure in your model sometimes. And this independence structure they mention here is oftentimes implicit in a lot of our models, whether you're doing machine learning or AI or whatever. At some point, you have to assume there is some kind of IID assumption, not IID on the observational level, but at some point you have to be able to write out your likelihood or your optimum algorithm. Your loss function will usually look like this, and that usually implies some kind of an independence assumption, whether you're being explicit about it or not. So again, if you're a frequentist, this would look the same. You assume that you have there's some generating process that you believe is generating your Y observations, and that process has some unknowns in there. You can call them parameters, you can call them weights or whatever. If you're a frequentist, you agree on this. In certain machine learning context, you also agree on this. If you are a Bayesian, you then say, well, we don't just care about optimizing or maximizing the likelihood. We're actually going to multiply it with a prior and treat our parameters as random quantities themselves about which we can make distributional assumptions. And that's the prior. And this is where the frequentists and Bayesians butt heads. And this is actually the only big difference between the two. If you're a Bayesian, you treat your parameters as random quantities. If you're a frequentist, you're not allowed to do that. But they usually agree on the likelihood, basically. And most models you can formulate as a frequentist or as a Bayesian isn't actually purely frequentist or Bayesian if you argue about it in the right way. It's more about what you do with the unknowns. Are you treating them as random? Are you assuming priors, basically? Because frequentists also use Bayes' law regularly, basically, even though they're not a Bayesian. There's nothing Bayesian about Bayes' law. It's all just conditional probabilities. You just become a Bayesian when you treat your parameters as random. It became useful to be a Bayesian when they developed Markov chain Monte Carlo, because all of a sudden you could do a lot of models that were mathematically intractable. You could solve for by drawing samples from the posterior distribution, and all of a sudden a lot of problems that were only theoretical for Bayesians became practical. One of the issues was what you do in the case of big data, and this article again tries to solve it. So here they say essentially you have this independence structure. If you split up if you write out the likelihood of all the data, you can split it up into these shards that they call S, basically, and this is essentially the mathematical underpinnings of that. They say how to split it up and why this would work in theory, basically. Now, in theory is one thing. They do highlight that the idea here, where's my mouse? The idea here is to use this mathematical equation. Now, here's the important thing. If each worker returned its posterior distribution as a mathematical function, it would be really easy because we could just multiply them all together. But remember, we're doing Markov chain Monte Carlo. We're not actually returning the answer you get when you do Markov chain Monte Carlo isn't actually a function. It returns random draws of the parameter. So, and when you combine those random draws, or when you look at those random draws, you draw a histogram of your estimate, and you essentially end up with a random distribution of the parameter. And now you say, well, I'm a Bayesian, so I think this is probably my estimate, but we have these random posterior draws basically. And the issue then is if each of the workers returns not a mathematical function, but essentially a histogram. From each of our S workers, we get a histogram. How do we combine them in a way that checks out with all the mathematics and everything that's coherent? And that's what the rest of this section is about. They say, well, how do we do that? And again, if we use the analogy of if we had a big data and we split it into 100 random shards, each representing a 1% sample, and for each of the 1% sample, we now have a parameter estimate. Let's say you want to estimate the probability of a user on Chrome versus a user on Firefox clicking on your ad, where an ad click is a very random, a very rare event. You might estimate, you might have lots of data. If you are Google, where this is where a lot of this was developed, you might say, well, we split it up into 100 shards, but in each of the shards, the parameter we estimate isn't significant. How do we do the meta-analysis? How do we combine all of this to get the real effect, to see if there is an effect? Are users on Chrome more likely to click on an ad than users in Firefox, basically? So here they say, well, one way to do it is you could just average all of it out, take the average effect, basically. And here they work on the assumption of if the posterior distribution looks near normal, basically. So this is a huge assumption. They say what would happen in the normal case, whereas all of your posterior distributions might not be normal, but we can say they are approximately normal. If you draw them, if you look at your posteriors, they all look more or less like that, right? They look normal. What would happen then in this perfect theoretical world? And then they do all the hard math to show, well, one way to do this, one weighting strategy is essentially to recombine your posterior distribution samples. So you've got your samples. So each of your workers return a histogram like that. If we've got 3 workers, we get 3 histograms of the parameter we care about. In this case, it's theta, is what they call it. If we have the 3 histograms, how do we combine all of them into one histogram, basically, one set of samples that we can use for our inference? And long story short, they essentially say this is the weighting. This is the weighting scheme. And then you'll notice there that this weighting scheme contains theta in there. It's essentially one of those, the estimate of theta we get from each of the worker. We will use essentially its variance to give it a weight, basically. So this, yeah.
Okay. So if I understood it correctly, so each of the shards would produce, according to this algorithm, the same number of samples. So
yes,
each one creates 1,000 samples.
Exactly.
And then you combine all of them, and all you get is another 1,000 samples, right?
Exactly that. Yes, yeah. You would have said, what would have happened if we don't split this up? If we ran this on a single machine, what would the answer have been? We didn't run it on a single machine because it's too large for a single machine. But what would have happened in the theoretical case if we had run it on a single machine? So yeah, it's exactly like you say. We draw 1,000 samples. We've now got, let's say we run it on 100 machines. We've now got hundreds, or in this case, we run it on 3 machines. We've now got 3 cases of 1,000 samples, 1,000 samples, 1,000 samples. But we just want one. We just want one. Mm-hmm. One answer of 1,000 samples, basically. So how do we recombine these ones? That's exactly what's happening.
What I found a bit funny, right? So in the prior, we take p of theta, so for each value of theta, and take essentially the s root of it.
That's correct. Yes.
Now that, first of all, of course, p to the first to the root of s is not normalized anymore, but I think that doesn't really matter because we re-normalize at the end, right?
Exactly. Yeah.
But what is strange is that if we take the higher and higher roots of a number, it becomes closer and closer to 1, right? So doesn't that sort of mean that the prior is widened on each individual machine to be more and more uniform?
Exactly. Yeah, that's exactly what is happening. And the reason for that is if you run it on a single machine, you essentially want to input a prior. Let's say that's the prior you want to input on the single machine. If you split it up into 3 machines, you have to be careful, because if you give each machine the same prior and you recombine, then what actually happens is you're recombining the prior by getting the prior to the power of s, basically. So as you say, when you do this root of something, it becomes wider and wider. The opposite of that is also true. So this is a case where you're avoiding using this prior, and in the end, when you recombine them, the prior actually looks like that because you didn't root it, basically. So this is one thing where they have to deal with that. What happens to a prior if you're doing this kind of split amongst the machines, basically? So yes, if you run it on enough machines, you're essentially giving each machine a uniform distribution, or nothing, or no prior information in the infinite case. As with so many of these things, you need to be careful when you're dealing with really large numbers, basically. I guess if we're using 50 or 100 or even 1,000 machines, it doesn't really matter. Larger than that, you start actually just using like then it'll stop mattering what you use here, because essentially whatever strong prior you wanted to assume will essentially become a lost in the numeric overflow or underflow, basically. So
what also was a bit funny is that so why are we not sampling each machine with the original prior, and then we just combine all of the values to say one big data pot, so rather than multiplying, just summing our data? What is it obvious why that is wrong?
I think this is why it's wrong, basically. It depends on how you want to recombine them, essentially. I think if you work through the mathematics, you might see you're actually implying some other assumptions in there. Like if you're saying we are doing it, we're drawing samples from the individual data, and then we're just recombining them into one big pot, essentially. I think it'll become clear why that might be wrong. It might not, but when you consider the problem of sampling bias, which I think they address in one of the sections here, because each of the little samples you draw, if they're too small, you might have a bias in this. You need to be careful about how you recombine them again. They do mention here that there have been other consensus strategies. One of them is one known as I think it's called little bags of bootstraps. So there's the averaging thing that you always have. They say importance sampling, normal approximations. So this article, they say, highlights 4 other methods for constructing it, essentially. So it might be that one of them is doing that. It's just in here, when you want to combine it in this exact way, you need to be very careful about the prior. But I'll be honest, I don't know enough about the mathematics, or I haven't really looked at this recently to be able to answer your question sufficiently. Yeah, I think it's just an interesting one when you write it out, when you write out what's actually happening in the way you're recombining. If you were to do it not just using the samples, but what's the mathematical implications of the recombining, you might end up with something that's not exactly equal to this thing you're trying to estimate, basically. And then you might have to apply another unbiasing on it, basically. So this is what they say how you should recombine. And the interesting thing is, if you again work through the mathematics, you'll see that the weights you get, if we again run it on 3 machines, if the one machine gives you a distribution like this, another one gives you a distribution like that, and the third one gives you a distribution like this. So there's more information in this one, essentially. Whatever is the shard of the data I gave this machine has more, let's say, useful information in it to estimate this. You would say when you do the recombination, this one actually carries more weight in the recombining it, essentially, because we're not learning much from this one. We're not learning that much here, but we're learning a lot here about the parameter, basically. So when you work through the mathematics, then you see it makes intuitive sense as well. And they don't just use the variance. In the reweighting, they essentially use, they stated here, this is the weight that they choose. The optimal weight is the inverse of the correlation matrix in between the samples internally for each of the shards, basically. So for each shard, you have to choose a weight. You have to weight the samples. And the way they weight it is by using the correlation matrix. You estimate from the samples from that shard. So in the example, you just have one parameter that you're estimating. The weight that shard gets in the recombination is essentially 1 over the variance of the shard. So 1 over that variance of the shard, which is what this is essentially saying. And that's also what this is to me, the intuitive nature behind that. We want to give more weight to the ones where we have more information, basically. And then if you have multiple ones, if you have 3 parameters, obviously you will have multiple samples. Like you saw, I might have 1,000 posterior draws for this one, 1,000 for this one, 1,000 for this one. And then you calculate your covariance matrix and you invert it, and that's the weight you use. They give some theoretical justification for why this is obvious or why this is true in the case where everything is Gaussian. They also use other ones. And let me check if anything else important in this one.
There's a question, but I think you already answered that.
So the weight decided on the standard deviation of the distribution from each shard. Yeah, that's correct. Yeah, that's where it's from. This is what they say how you choose the weights. And this is quite an optimal way to do it. It's also an easy way to calculate it. This weight. So makes intuitive sense, easy to calculate. And now the problem has become embarrassingly parallelizable.
That's a question.
Yeah.
Why variance and not entropy?
Is
it just because that's how they get the math work?
I think it's because the way you add independent Gaussians is by summing their precisions.
Is the Gaussian assumption then?
Yeah. You might another way might be, an interesting article might be to see if they've tried this using entropy, essentially. You'd probably end up for Gaussians, you'd probably end up getting something similar, because a lot of the interesting stuff is what happens when it's not Gaussian, basically. They did do some tests here. Usually when you have enough information in the data, what you end up with are posterior distributions that all look more or less like that. They might be slightly skew or something, but you could essentially squint your eyes and pretend it's Gaussian. If you're getting very weird priors, if you're getting things that are multimodal, basically, obviously then you start running into issues. Then you might have to split that up or do something else. But usually when that happens, you should probably reformulate the problem. This is, I think, why they use this. In this case, it's easy when everything is Gaussian. It might be interesting. I'll see if there's an article out there that says if you use entropy, essentially, because that's essentially, I would say, a better way to measure the same thing, right?
What is actually the entropy of a Gaussian, right? Because entropy is, I think, strictly only defined for a discrete distribution. So you probably would say something like differential entropy, which
you'll have to
funky anyways.
Yeah.
But what I found funny is that these G's are essentially random, right? So you get a batch of samples, and you say the first sample I essentially randomly draw. I call G equals 1, the next one G equals 2.
Yeah.
And I would not be surprised, of course, if you take these samples and you were just randomly reorder G's for each one, you would get a slightly different answer. I wonder whether one could combine permutations of these to get an even more good answer.
That's an interesting question. A great application is a good way to single out a useful prior, which is very challenging. That's true. Yeah. Like I said, I'm actually quite sad that this technique hasn't received more interest, because I think there's some interesting ideas here that obviously it was developed for a very niche field, which is generative Bayesian models, which is essentially the thing that makes the model complicated is the fact that you've got hard assumptions on it, complicated assumptions on the model, complicated generative assumptions that and your data might be continuous as well, instead of just doing classification or whatever. So this is a niche field, I guess, or a niche use case. It's used mostly in academia and in some wings in companies like, let's say, Google and Facebook, where they care about inference. They do A/B testing, and they really care about the parameters. They're not just trying to predict. They want to see what makes the difference. I have a theory that people who use Chrome on a Friday is more likely to click on an ad than an individual who uses Firefox on a Monday. I need to prove this so that we can invest money in it and make our ads better or whatever. So this is where this is this application essentially, and I do think there's a lot of use in there, which is why I was keen to present this in a machine learning group, because cross-pollination, I think, is useful. So that's the theoretical underpinnings of this. The rest of the article deals with some examples. And so in section 3, they actually give more theoretical underpinnings where they say choosing weights is, like I said. They quickly go through other strategies and say why they chose this one. Fairly interesting. And they do say here the big caveat is consensus distribution based on averaging are obviously limited to continuous parameter spaces. This is hard to do when you don't have a continuous parameter space. Like they say here, if you're doing the Dirichlet mixture distributions or regression models with spike and slab priors. Now, I think to many people, this is going to be a huge caveat, basically, because a lot of people do classification, or they want to reformulate their problem so that it's a classification problem that you can solve without continuous parameter spaces. So I think this is the biggest gotcha of the article. If your problem is a continuous parameter space, very good. If it's a discrete one, this is probably not the thing to do there. You should probably just use neural nets or some other classification algorithm that's better suited for it. If you can't, if you absolutely have to assume some continuous generative process, like the examples I highlighted, this is a good way to do it. They also go and say, right, more complicated models, nested hierarchical models. So this is where MCMC really shines, is if you have these multiple nested hierarchical models where you have groups of groups of groups, and each group has its own prior assumption, and each prior has its own prior. The problem is here, they say, you need to be careful how you sample then. I'm not going to go into the detail here, but they say you need to be careful how you sample. Once you've solved it for one level, it can nest as needed, basically. Usually you won't have to nest it. They just say, when you draw the shards, you have to make sure that each shard has a little bit of information to be able to estimate all the parameters, basically. You can't have a parameter in your model somewhere that represents, let's say, a Tory voter in a Labour district, and you want to estimate how likely they are to vote for something. And when you're estimating it, when you split up the shards, some of the shards have no information about these individuals in there. That makes it hard then. Like, each shard has to have a shot at estimating every one of the parameters, basically. So you have to be very careful when you draw a sample to draw a representative one. And this is another one of, I guess, the caveats. If you have groups and groups and groups and levels and levels and levels, where essentially when you try to draw a sample, a lot of the groups at the lowest level have zero information in them, or no samples in them, then this thing also fails. Not horribly, but you can't estimate anything without information. That's what this is essentially saying. They also go into non-parametric regressions. I won't go too much into this idea because I'd rather get to the examples, because I think they're more interesting. And they know this is where they discuss the issue with if you have small sample bias, essentially. If you draw a sample that is so small that every sample is ridiculously biased, essentially, like if you have 100 humans and you're drawing a sample where in each one you've got only 5 people, you might have some samples where all 5 people in the sample are old people, or all 5 people are males, basically. So that specific sample is very biased. You can't hope to estimate the parameters for, let's say, a female user if your sample only has males in it, basically. So this is the kind of thing, again, we have to be careful about the sampling and make sure that your samples, at least, this is what makes this hard. Once I read about this process, I thought, oh, this is too good to be true. I could just make all my problems embarrassingly parallelizable. You can't. You have to be careful in how you draw the sampling. Once you've got all of that out of the way, so again, here they say if you have a sample, you usually have to adjust it for the bias. But if you draw large enough samples or unbiased samples, you can just ignore all of this usually. But you have to be careful. There's always going to be some kind of no free lunch, basically. They go into the examples where they show how this works. So for each of the examples here, they're essentially doing a play scenario where they say we run it on a single machine, because we have a big machine at Google. Then we split it up onto 100 workers and see what would the answer have been if the problem was too big to fit on a single machine. This is, I think, a very good way to look at the examples, because it's a theoretical case of what's actually happening behind the scenes. We can see what's actually happening. They go one step further, and all the data they use here, they simulate themselves because they know the parameters. So they want to see, can we estimate the parameter on a single machine? If we split it up on 100 machines, are we estimating the same ones, basically? So this is like the perfect example. That's unrealistic. But if this algorithm, if this MCMC consensus algorithm doesn't even work in the perfect case, it hasn't got a shot in the real world. The first one, they just do a binomial one with a beta prior. I think this one's uninteresting. I'm just going to skip it because nothing much comes out of it, which I think is worth discussing heavily. The second one is also where they say another very theoretical case where you have a Gaussian distribution, what would happen if we estimate it? These examples are so theoretical, I don't even think they're very useful other than just checking some ground truth assumptions. The interesting things come in 4.3 when they start saying, right, let's say we have a logistic regression where we might say, this is like, again, because this was developed at Google, they have this example, logistic regression is a widely used model for internet data because you want to see when someone clicked or mouse over or whatever. You're trying to estimate events. How are events, what influences events? They care about clicks because if they know who's going to be more likely to click on an ad, it means you can charge more for that ad in the way that you do the auctioning. This is also why a lot of the models they use are like little logistic regression models, because they have to do this, they have to predict right before they show you the ad what's going to happen. How likely is it to be clicked on? And small logistic regression models is usually quite nice for that. So again, they make a model where they say these are the actual real values, the parameters. These are the actual coefficients for the model. This is some simulated data. Again, this isn't by any stretch of the imagination a big data problem. It's a thing you can do on a single machine, but they want to see how well the model performs essentially. So after this, I will go to like a special example that I think they should have included in the paper that they didn't, but that's also very interesting. So they just go and say the single machine. So these are all the estimates of the parameters, of the 5 parameters using a single machine, which I think is given in black. They give the single machine in black, and then they give the other ones in the multiple colors. Logistic regression with 100 observations per worker. These are the posteriors. These are where they ended up if you plot them on a scale that makes it easy to view. And this is if you plot everything on the same scale, basically. So you'll see there, the blue one, I guess, is, what's the blue one? Single machine estimate, and the consensus one under the various weighting schemes. So these are the various weighting schemes, basically. So as you can see here, the blue scheme is the equal weighting scheme, where you're just averaging it out naively, basically. So we see that doesn't work. And then this is where they weighted using a matrix of the variances. The scalar one is where they say we don't use a matrix of the variance. We don't use the covariance matrix. We just use like a scalar of all the variances to weight it essentially. So you'll see the naive one is blue, the green is slightly better, and then the red one, the matrix one, is where it works best. And then the black is the actual answer, the machine answer, basically. So this is just for them to get an idea of what's working best. So it looks like it works well for this problem. Then they go on and they do the same thing for a hierarchical model. Again, this only really works if you have these kind of generative models, where you have a model where you say, I believe that Y is a Poisson distribution, the number of events, the number of clicks, the number of users, whatever. I want to model that using a Poisson. This is my model. These are the dynamics of my model. If I were a Bayesian, and I'd be chatting to a frequentist, we would agree about this. This is a good model to fit. Where we stop agreeing is where the Bayesian says, right, now let's assume some priors and estimate the parameters, basically. That's what's happening here, as always. For this model, again, they show the same kind of thing. Works well on the single machine and works well on the individual. If you split it up, basically, you essentially get the same answer whether you used one machine or whether you used the consensus one. This is essentially proving that splitting it up onto 50 workers, you get exactly the same answer as if you would have run it on one machine, basically. And that's what we wanted. We essentially wanted a way to make the problem embarrassingly parallelizable. Again, I'll just rush through this because I guess this is where it becomes interesting. Another one where they show larger problem with more shards, basically, overall consensus. The main takeaway here is this single machine and the multiple machines look about the same. They overlap overall in consensus. Last one, 4.5, is where they veer outside of their comfort zone, and they say, what if we wanted to do non-parametric regression? So non-parametric regression is essentially the Bayesian nod to saying we don't care about the dynamic of the process, we just want to do a prediction, basically. Usually when you're a Bayesian and you're doing non-parametrics, you're using Gaussian processes, Gaussian all the time. Gaussian processes are very strong, luckily. So this is one way to write the Gaussian process. I think there was an article from 2013 or something that proved if you have a neural net and you make the hidden layers infinitely wide and infinitely deep, you're essentially approximating a Gaussian process or something like that. So Gaussian processes are quite strong. The interesting thing here is they show that the time required for using standard MCMC versus consensus MCMC, if you split it up into more and more shards, or if you have more and more data, it's possible to do this problem using ordinary standard MCMC methods, which is why people use neural nets for this, right? But this actually works quite well, the number of shards. And then they also go on and they show an interesting result where, I'm not going to go into too much detail here because we don't have much time left, but they essentially have this interesting result where for this Bayesian additive regression tree, doing the consensus algorithm actually fits the data slightly better than the single machine algorithm, because remember, we simulated the data, so we control what we do. And they say here they believe it's because it's for the same reason that I guess a random forest works better than a tree, basically. When you're splitting things up, it sort of has that way of magically reducing the bias, basically. Very interesting result. But again, this isn't what they care that much about, which is why this is an afterthought. Now, before we get into the discussion, the example I think they hadn't included here, which is one I ran on my own laptop at home just to get excited about it, is I said, what if we have a logistic regression for a very rare event, basically, where the event is so rare that we can't, if we split it up into 100 samples, 100 shards, none of the shards has a way to actually statistically significantly identify the effect is there. Like I said, let's assume there is a real effect between like Firefox and Chrome, but we need lots of data to prove it, basically. So I simulated the data, so I know the effect is actually there. I made the effect a significant one, but very small, like very, very artificial, like really near zero, but still significant. And you can't estimate it on any of the individual shards. But if you run the consensus algorithm, you get the parameter. It estimates as a significant one, and it's also the right estimate, basically. So that made me very happy, because if I ever have this really rare event, as long as I can draw the shards properly, as long as I have a representative sample in each of the shards, you can do this meta-analysis and discover small but significant events that you otherwise wouldn't have. I think that would have been a good addition to this article. But anyway, so then they go into the discussion.
Can I ask a question, though?
Yeah, please.
I just realized this may be a stupid idea, but maybe not. So what if you approach it from the opposite direction? So let's say we have very little data. We only have one shard.
Yeah.
Right? That's our actual data. So that the rare event is not detectable. Can we generate more shards, but only replicating the rare event everywhere? Every other part is generated, or actually, maybe we have so much data for non-rare events, we can split it, but only copy the rare event in some way.
Yeah.
And then run this algorithm. Will it suddenly be visible as significant?
I guess, yes. So I think this is what they do when they do upsampling or downsampling, essentially. You can usually you can usually, I think there might be some theoretical caveats of if the model is very hierarchical with lots of layers, you might have to be careful how you do this, but that might be like one way to do it. It could also be a case of if you have a shard and the shard represents all the data we have in the world, you can use that to do like a statistical power study, as in ask yourself, how much information would I need for this to become significant, basically? Like how much the data would I have to collect? If I believe there's an effect there, and the effect is close to the one we estimated, it's just not significant, basically. We estimated an effect, we believe that might be the real effect, but we don't have enough to prove it. Like, how much would I have to collect, basically? You'll just have to check that you're not making up new information, basically making up new data as you go along, because usually when you have a conclusion that's not significant, the only two ways you can add information in there, information in inverted commas, is by making more assumptions or by adding more data, basically. So you just have to be careful that you're not implicitly making some kind of an assumption by just adding in the data, because we're not explicitly making an assumption, it might be implied by the math, basically. Like I usually say, if you're doing linear regression and you use least squares estimation, you're implicitly making the assumption of a normal distribution or normal errors, and you can prove this by showing that normal distribution with likelihood estimation is mathematically equivalent to least squares estimation. So whether you're making it explicit or not, there might be some assumptions in there, and that's where I'd be careful. No free lunch thing. I see there's a question. Breaking the problem is smaller size is a bit like classification, but incorrectly. I think with consensus, you can tell early on that which information is more important, so you learn to classify earlier with some shards. This information is summed at the end, so in a sense, you're ensembling, I think. But with separate machines, you have regularization as well. Yeah, I think that is a good way to think about it. It's again, it's a thing that comes up over and over again, is when you ensemble, when you combine, things work a lot better, basically, which is quite nice. In the discussion here, what they say essentially is this is more research is needed. They say here it works for more research is needed to see how this will work if the models are non-Gaussian, basically. It looks like it will work. Consensus Monte Carlo scales well. It can be used in a cluster of computer. It's a useful technique because it looks like it works. But more research would be needed to see what are exactly the caveats. That's what they say here. There's a long list of open questions that needs to be addressed about this. More understanding when we have posteriors that's very far from normal, basically. To the extent that averaging fails in non-Gaussian models, other methods of consensus should maybe also be explored. Not much exploration has happened on this. After this, it's a field that has stagnated since 2013, which I think is a shame. They also say, again, the weakness that it's limited to unknowns of fixed dimensions in continuous parameter spaces, and the issues you have with the regular MCMC, like label switching and changing number of dimensions, they get exponentially harder in consensus, basically. If it's hard for ordinary MCMC to solve, it becomes much harder in consensus MCMC. One thing they do say, and I think this is a takeaway for everyone everywhere, is if you're unsure about the theory, try anything you want to try first on the simulated data set to see how well you can identify things in the ideal case, basically. And this is a thing that I think you should be doing even if you're not doing consensus MCMC. If you believe there is a model that can identify something in your data, do it first on a data set that you simulate, where you know the ground truth, basically, and see whether it works for that example. Because if it's not even going to work in the perfect example where you control everything and where you essentially play God and set the ground truth and know it, basically, using it in the real world is just going to introduce more headaches, basically. So this is what I like. They say here as well, before you run it on a data set, simulate a data set that has the characteristics you would like to identify, and then see if it works on consensus MCMC, and then run it on your real data. So, which I think is quite smart. And that's the paper. In the future, if I present again, I'll probably do some more stuff around probabilistic programming languages and interesting things you can do with them. And yeah, that's my story. Any last questions?
Oh, thanks, Dirk.
Thanks, Mohan.
Very interesting paper. Great presentation.
Yeah, more programming, please. Probabilistic programming. That's really really cool.
Yeah, I'll do that next time if I can find a good article. Yeah, but I'll do some probabilistic programming. Yeah. Have a good one. Thanks, everyone. Bye bye.
Bye bye.
Bye bye.
Bye.